inviting me for the seminar. Okay. Okay. So I hope everybody hears me well. If not, you just tell me. And as Chris told, if you have some questions, don't hesitate to interrupt me and point. So the results that I will show today, we obtained in collaboration with many different people. Some of them are listed here. I might forgot somebody, but especially I would like to thank help with two large teams of two large field experiments, one in Massif Central that we're running right now, another in Kamchatka now 10 years ago. Okay, and I will speak about volcanic seismicity, so it will be about volcanoseismology, and I will start with, how can I do this? With some short introduction about volcanoes and volcanology. Okay, so we're living in Europe, and when we think about volcanoes, we're thinking about hazards, eruption, and for example, one question that we can ask volcanologists, uh, so where we can expect the next catastrophic eruption in Europe. And here I show some obvious answers where we know active volcanoes in Iceland, in Italy, in Sicily, like Etna, or around Napoli, where we have Vesuvius, a conflict degree. Okay, so today, I'm sorry, I will not speak about Iceland and Italy volcanoes because I never worked on it. And I think in Italy, there are much more people with knowledge about this. So I will rather speak a little bit about some less obvious volcanic objects, like these Holocene volcanic provinces existing in Europe. For example, we have one in France that is called French Massif Central, and you can see there are some volcanic edifices, and another one somehow very similar is in Germany, Eifel province. Okay, and basically they are considered today as dormant, but we know that they were erupting not so recent, not so late, so relatively recently in geological time. For example, in Eiffel, only 13,000 years ago, there was this huge eruption that is illustrated here with 6.5 kilometers of erupted material, geological estimation, some important tephra deposits. So if something like this repeats today, it will be really a major event in Europe, and I'm not sure if we know how to deal with this. So more generally, how we know which volcanoes are dangerous and if we can expect catastrophic eruptions from these volcanoes. I try to illustrate this with this maps. Basically, we have information about past eruptions, some from history, mostly from geology, and that is represented here. So all dots on these maps are some important volcanoes. Big dots are supervolcanoes that produced really huge eruptions. As you can see, very important parameter to characterize volcanic eruption is a volume. Okay, for example, Vesuvius, famous eruption that destroyed Pompeii, its volume is estimated between 1 and 4 kilometer cube. It's huge, but it's relatively small compared to some major historical and geological eruptions like Tambora or like Toba. Okay, so in volcanology, volcanologists developed this quantitative scale to characterize volcanic eruptions. It's called volcanic explosivity index, and basically it's logarithm of volume of erupted material. Okay, so in volcanology, we deals with volumes. Okay, now next thing about volcanoes, this past eruptive history is what we learned from geology at the surface, but volcanoes that we see at the surface are only the tip of the iceberg. And actually the major processes that lead to volcanism occur at depths. So in the mantle and the crust, basically magma I believe to originate in the mantle, then they ascend through the crust, through the complex volcano-magmatic system to the surface, and this what leads to eruption. Okay, so therefore to know how really volcanoes are potentially dangerous, we need to know what happens there at depths in the crust and the mantle. So basically, today, for many volcanoes, we know past eruption rates estimated from history and geology, but we have very approximate idea or not knowledge of, at all about how much magma is stored at the crust, what is the architecture of this magmatic system, so where this magma is stored, and also another important question, if the magma continues to be supplied from below. Okay, and so for these deep roots of volcanoes, seismology, one of the main methods that provides us with the information. This is what I will speak today about. So volcanoseismology, so in a very large sense, is aimed at understanding volcanic eruptions. So it ideally we would like to understand when and where next important or catastrophic eruption will take place. Obviously, we would like to estimate the size and impact of these eruptions. And for this, we need to understand the relationship between the seismicity that we observe on volcanoes and the eruptions. And again, volcanology, as I already told, is about volumes. So what we need to understand about volcanoes, we know erupted volumes, but we need to understand volumes stored at depths. And also, we would like to understand these magma supply rates. Okay, so I summarize it here. Schematic representation of magmatic system. We have as input deep magma supply rate, and at the surface we have eruption rate. This is again something that we know from geology, but from seismology we would like to understand the geometry and volumetry of the magma. For this, we typically use seismic tomography. It's not something that I will speak today. But then we also would like to know how much magma is supplied from below. And for this, we can use deep volcanic seismicity. And this is exactly the topic of my study today. Okay, so I will speak about seismicity occurring at more or less between the mantle and the crust. Okay, and again, volcanology is about volumes. So I here just give you some key numbers about volcanic system we may study. For example, most active volcanoes on the Earth, like Hawaii or supervolcano Toba or volcanoes in Kamchatka, in very active subduction volcanoes, can produce around 1 cubic meter of lava per second. Okay, it's huge. In terms of if we average this in years, this will give us such eruption rate. For less active volcanoes, like for example, Piton de la Fournaise in La Réunion or Katmai volcanic group in Alaska, it's an order or two orders of magnitude less. And then if we speak about some dormant volcanic provinces, like for example, Chaîne de Puy in the French Massif Central, it's even much less. It's really small. Okay, so but this is again something that we know from geology. What we may expect at depths. For this, there is such a concept in volcanology that volcanologists call intrusive to extrusive ratio. Basically, the idea is that the lava erupted at the surface is only some portion of the lava of the magma that was injected from below, because a huge portion of magma that was injected into the crust remained forever trapped in the crust. So therefore, if we have, for example, 1 kilometer cube at the surface, we can expect 2 or 12 more times of magma injected from below. Okay, so these numbers for this ratio between 2 and 12, I found this in some publications. I would say these are educated guess because again, the volumes really trapped in the crust, it's very difficult to know. But this is what volcanology typically operates. And then what we can say that for thick crust, we expect more magma trapped at depth. So this intrusive to extrusive ratio will be larger. Okay, and so if we take this into account, these are deep magma supply rates that we expect at the crust mantle boundary. Okay, as you can see, at most active volcanoes, we can expect up to 1 kilometer cube per year, which is really huge. Okay, so now let's speak about volcanic seismicity. So here is again, this is some real seismograms, and this is a sketch. Okay, this is from some relatively already old paper that shows some typical volcanic seismovolcanic signals, and they can be separated in two big groups. One group is these typical small earthquakes that are called volcano-tectonic earthquakes. They basically represent the faulting in response to stresses caused by magma overpressure or motion. Basically, when magma is active, it imposes some stresses on surrounding media, and small faults place, and this generates these earthquakes that are in all characteristics very similar to small tectonic earthquakes. But then we have many other types of signals that I regroup into this category as low frequency seismicity. Okay, they called low frequency because they're typically characterized by lower frequencies, not more than 10 hertz, which is for small earthquakes is really low. And then this low frequency seismicity is believed for many reasons to be directly caused by processes within magma, pressure changes, viscous forces, and so on. And so this, for us, if we want to characterize processes in the magma, this low frequency seismicity is potentially much more interesting. Okay, now after this introduction, I will start to show you some real data on which I'm working with. And for this, I will start in Kamchatka, the place where I worked for several years in the field, and very interesting from tectonic and volcanic point of view. Basically, we're interested in this place. You can see already there is some topography here, and it is it turns out that tectonically there are two peculiarities here. First, there is this corner of subduction slab. You see there is the end of Aleutian trench, and then end of Kuril-Kamchatka trench, and basically the Pacific plate slab ends up here. Okay, and then another very interesting feature is this mountain chain arriving and subducting just beneath this place. And this is a mountain chain that originates in Hawaii. From Hawaii, I mean, this is the volcanic chain that was created by Hawaiian volcanic plume. Okay, and as a result, we have very significant volcanic activity here. Now, when I zoom on this region, this is a photo from the space station. Okay, and you can see in this relatively small region, you can see the scale. So the distances between volcanoes are around 50 kilometers. We have 13 large stratovolcanoes and uncountable amount of small volcanic cones. And 4 of these volcanoes are today active, and some of them very active. And the major volcano is this, Kluchevskoy, that gives the name to this volcanic group. This is the volcano, to tell you, geologists estimate that its age is only 8,000 years, and today it's almost 5,000 meters high. So it's really very, very, very active volcano. Okay, so and this is the reason to work in this volcanic group, because it's one of the most active objects with a lot of earthquakes and tremors. Okay, and here are the data that we use in this study. So I will mainly use the data of this experiment that we call KISS, Kluchevskoy Investigation of Seismic Structure. This is an experiment run by Russian, French, German groups 10 years ago during 1 year, and when we installed more than 100 stations in this region. And what is also interesting, all this data now stored in Geophone Data Center, open access. So if somebody is interested, it's available. Okay, and so I will start to show you some results of analysis of this data. Okay, as I told, the network operated almost 1 year from September 2015 to July 2016. And first thing I will show you, it's a very recent result obtained by Wei-Fan Lu, a postdoc in Grenoble, who applied modern AI-based detection methods to this network. Things like FaceNet and associators. If you have question, I think Wei-Fan is here, he may. answer. And so the catalog he obtained contains more than 10,000 events for less than 1 year. It's 10 times more than handmade catalog by local observatory. And the distribution of earthquakes along this south-north profile is shown here. And basically we see that there's a lot of seismicity in the crust, but then this very dense and huge cluster at the crust mantle boundary. And basically, we have this shallow volcanic seismicity, and this is the object I will talk about. This cluster is a cluster of deep, long-period volcanic earthquakes. Okay, now I'm showing you why we call them deep, long-period earthquakes. Deep because they are located at 30 kilometers, more or less, depth at the crust mantle boundary, and long period is illustrated here. I use this station located very close to this Khrushchevskoye volcano, and this is just one example. I think it's how much less than 1 hour, and we see that we have sometimes these very intense swarms of earthquakes, and all these earthquakes come from these depths. And when we zoom on some of these earthquakes, we can see P and S wave was actually S minus P time of 5 seconds, which corresponds more or less to this depth, 30 kilometers. And then we see that they are really depleted in high frequencies, and we can see this in Fourier transform. So this is why they call deep long period volcanic earthquakes. Okay, so this is the first catalog I will analyze, but also on volcanoes, as you know, apart earthquakes, we also record a lot of tremors, nearly continuous seismic signals that cannot be characterized with discrete catalogs. So for this is the work that we did already some time ago by Cyril Journeau, my former PhD student. So, and we developed this method that I will not, I don't have time to explain it, but basically we use the whole network covariance matrix to detect tremors, and the detection is shown here. Basically, we use the spectral width value. When it's low, when it's showed with these orange colors, we have tremors. Okay, we can see that during this period of operation of the network, we have at least 2 significant episodes of very strong tremors. Okay, and next thing we can do, we can locate these tremors. Basically, we compute cross correlations and back project them in space and depth. And here are just some examples. The red window shows the window that we analyze, because when we analyze tremors, we analyze rather long windows. In this case, 20 minutes. And so, when we locate this window, that is actually, we know, by the way, it's composed of these deep long period volcanic earthquakes, where it locates not with very high precision because we don't have separate PNS waves, but still we see that it's really at depth, it's not at the surface. So, and then if I take another example of some continuous tremor, it really locates at depth, okay? And then another tremor episode, again, it's near the surface, but it's not beneath Khrushchevskoye volcano, but beneath other volcano. So we have this method that allows us to detect and locate these tremors with reasonable precision. Okay, so, and here I show you the result of this location. So we analyzed this more than 10 months of data, identified all time windows that were characterized as tremor detections, and plotted the density of the hypocenters. It is shown here, and we see that mainly we have these tremors concentrated beneath main volcano Khrushchevskoye, but some beneath other volcano Tulbachik, and we can compare this with distribution of earthquakes and with this DLP cluster, and we can see that, yeah, there are also a lot of tremors in the same area where we have these DLPs. Okay, so these are actually complementary phenomena, and we need to use complementary methods to obtain full information about the seismicity. Okay, so this is the special representation of this 2 catalog. Now, what is very interesting is to see how things vary in time. And this is what I show in the next slide. So I will compare this DLP catalogs. By DLP, I mean isolated this cluster. I only took earthquakes here, and I plot their recurrence in time. So you see, this is the number of earthquakes detected per minute. And basically what we see that first we have apparently some increase of activity, and then suddenly we have no earthquake, then again activity, and then no earthquake. And when we compare this with tremors, we understand why, because tremor catalog is shown as depth versus time. The dates are the same here, but here you see the tremor depths from 0 to more or less crust mantle boundary. You can see initially we had very few tremors and mostly deep tremors. And then suddenly we started to have a lot of tremors with a lot of shallow tremors. And when we have strong shallow tremors, our seismograms are completely polluted by these tremors. We cannot detect many earthquakes. This is why we don't see earthquakes here. And then we have some quiescence in tremors, and we again could detect earthquakes. And then again, we didn't, the tremors started, we have earthquakes. But what is interesting, these tremors, they are obviously related to volcanic activity. So first we had some volcanic quiescence, then we had an episode of volcanic unrest with a lot of shallow tremors, then it stopped, and shortly after it restarted, and then it was followed by eruption. So somewhere in April, the Kluchevskoye volcano started to erupt. Okay, and basically we see this behavior of our system. We have quiescence, but with increase of deep long period volcanic earthquakes, and especially we have this strong burst here a few weeks before this unrest. Then after this deep part is very active, we have unrest in the whole crust with activity transferred to the surface. But then we have some quiescence, again unrest, and then eruption. Basically, we see this interesting behavior that this deep long period earthquake somehow precede shallow volcanic unrest and eruptions. Okay. And to illustrate you that this is true, I show you here the results of my previous paper that we did with using a permanent network on the same volcanoes, where we detected these deep long period earthquakes and other long period earthquakes by template matching. And we have 2 years of data. And what is interesting, we can see when we look at the activity of these deep long period earthquakes, we see that it oscillates, it increases, decreases, increases, decreases, increases, decreases. And when we compare this with the eruptive history, because during these 2 years there were three eruptions of this volcano Bezymyanny, and one huge eruption of this volcano Tolbachik. Basically, we can see every time we have increase at depths here, we have some relatively quick transfer of pressure to the surface, an eruption, increase eruption, and then increase eruption and another eruption. So we have this idea that this deep long period volcanic activity precedes the shallow unrest and eruption. So for this reason, we can propose the following interpretation for it. So basically, we have our volcanic system, and at some point, we have some injection of fresh magma to this level beneath the crust. And obviously, it destabilizes this area, and this is why we start to have deep long period seismicity. Okay, and then, oops, sorry, and then after this, the pressure generated by this fresh magma somehow is transmitted through the whole crust to the surface, and then we have shallow unrest, and at some point we can have eruption. Okay, I think this is very logical interpretation for active volcanoes, and this indicates why this is interesting to look at this deep long period earthquakes and tremors, because this is actually the early precursor to eruptions. Okay, so this is a very nice story, but now I will show you the result of other study done by US colleagues, not mine, that proposed another interpretation. So in this case, they were looking at a dormant volcano. So this is a group from USGS, I mean Alaska and other volcano observatories. And they were looking at Mauna Kea volcano in Hawaii. It's important to mention that Mauna Kea volcano is located here in the northern part of Hawaii, big island, while the active volcanism and actual plume is located in the southern part. So Mauna Kea today is really dormant. Okay, and the last eruption was almost 5,000 years ago. Okay, and here the signals show the deep long period volcanic earthquakes recorded by this station, Yapona here. And it's really impressive because you see this very regular earthquakes. Okay, and so you see this vertical line are these DLPs, and when we zoom, we really see that these we see P waves, S waves again, almost for nearly 4-second S minus P time, and the really dominated by long periods. Okay, but then what is remarkable here is this regularity, and it is illustrated here. So these colleagues, they measured inter-event time, and you can see it remains extremely stable for many days and even years. Okay, basically, contrary to what we have seen in Kamchatka, where these deep long period earthquakes occur in short bursts and very regular in time, here we see some extremely regular, nearly periodic process, okay, that would suggest that we deal with some kind of stationarity in the system. This is why the interpretation of this low frequency seismicity in this region by colleagues was completely different. They suggested that this seismicity is not linked to pulses of new fresh magma, but is linked to or caused by the outgassing of cooling magma. Basically, they suggest that there is this magma body that has been deposited sometime geologically some time ago, and now it's in a cooling state. And when magma is cooling, there is this process called second boiling when crystal grows and gas is exsolved, and then this gas is somehow slowly and stationary filtering through the whole magma body. And when it gets out through some valve system, this generates this very regular, nearly periodic pulses. Okay. Again, I think this interpretation for this particular volcano seems quite reasonable. So now I will present some intermediate summary of observations of this deep long period volcanic seismicity in the world. First of all, I have shown you only 2 volcanic systems, but this kind of earthquakes have been reported, I would say, almost everywhere. So in Indonesia, Japan, Alaska, Cascades, Iceland, Eiffel, French Massif Central, and I'm sure there are these earthquakes in Italy. I just didn't found quickly the publications. So these earthquakes, as I told, they observed close or beneath volcanoes. Their occurrence rate can be very different from many thousands, like in Kamchatka or Hawaii, to just a few earthquakes per year. So they observed between uppermost mantle and mid-lower crust. For in some volcanoes, like for example in Eiffel, they really penetrate into the crust. So what is interesting, I don't have time to show in details, but it's difficult to estimate focal mechanisms for these earthquakes because they are small, signals are often noisy, but there were several attempts to do it, and most of the study reports significant volumetric component, and this will be important in the future. So, and obviously, origin of these earthquakes is linked to processes within the magma, but there are 2, as we have seen, different interpretation. In Kamchatka, we suggested that this seismicity is linked to pulses of fresh magma. In Hawaii, it is interpreted as a cooling of stagnant magma body. Okay, so this implies that when we study this kind of seismicity for a given volcanic system, we would like first to understand what of these scenarios is more plausible. And I think one of important features is stationarity versus regularity, because this kind of scenario, at least in Hawaii, resulted in very regular occurrence, while this kind of scenario resulted in very irregular bursts of earthquakes. Okay, so this is the first question. And then the second question would be, if we consider this hypothesis of fresh magma as likely, this is very interesting and important for understanding how volcanoes work. And in this case, we would like to use observed signals to estimate magma supply rate. Can we do this? We will see. Okay, and here I show you the example of very recent study where all these questions were raised. So this is our recent experiment in the French Massif Central. So French Massif Central is located here in south central France. And there's this volcanic chain here with the most recent volcanoes of the chaîne de Puy. And today it's considered as a dormant province with the latest known eruption 6,700 years ago. Okay, and to study this region, we installed, starting in 2023, this network with many seismic stations. And one of the things we started to do, we started to detect earthquakes, and some of detected earthquakes are shown here for this period. And I just show you that among these earthquakes, there were these deep long period earthquakes. So for this, I compare one earthquake located here shown with the blue point with another located not so far from it. Both have magnitude of 1.4 more or less. This deep earthquake was located approximately at 30 kilometers. Again, this is a boundary between the crust and the mantle, and this is really in the crust. And you can see, just looking at the seismograms, that the frequency content is completely different. Okay, and when we plot Fourier spectra, it becomes very clear. So to classify all earthquakes in low frequency and not low frequency, we just define two frequency ranges, low frequency, high frequency, and we compute energy ratio from signals between these two frequency ranges. And and it is shown here. You can see. So this is example for some stations. We have, for most earthquakes, some regular trend with a lot of high frequencies, but then with some clear outliers. Okay, that are these low frequency earthquakes, and in total, we found 10 of them. Okay. And here are their locations. They are all actually located at this deep region at the level of Moho, maybe a little below, a little above. And 9 of these DLP earthquakes are located beneath this Puy de Dôme volcano. That is actually most famous volcano of Chaîne de Puy, most dominant volcano in the region, and that has last eruption relatively recently in geological time. And then we have this one that is located beneath other volcano that is known like Lac de Gaudivel Lake. And again, it is known volcano that has been active at least 130 years ago, but maybe later. Basically, we found these earthquakes beneath 2 known volcanoes. Okay, and for people working on these volcanic provinces and living there, this was really important. After we published our paper, there were some amount of publications in media, and we were contacted because basically idea before was that this is a dormant volcanic provinces without no volcanic activity, and these observations was the first direct evidence of deep magmatic activity beneath these volcanoes. It indicated that they are not dead completely, that magma is still moving, transporting, something happens. And so then the next question, so what is this? Is this stagnant magma that is cooling, or maybe some new magma is arriving? And for this, I show you the times of these earthquakes and also examples of some waveforms. And my point here is that occurrence of this earthquake is not stationary in time. I mean, these dates are rather random in time. And when we look at every individual earthquake that you can see as maximum signal here, actually, it's not a single earthquake. It's always, almost always a short burst of many earthquakes. Basically, we have this very irregular pulses, irregular bursts, and non-stationary process. So this is why it may be plausible to consider that these deep long periods of earthquakes beneath the chaîne de puits are caused by pulses of fresh magma. At least we should not reject this possibility if we want to be cautious with understanding of what happens beneath these volcanoes. So the next question is how strong are these pulses? So because some people, when they read papers about our publication, they called us and asked, oh, what should we do? Will volcano erupt tomorrow? What happens? Okay. And for this, there's one simple way to answer this question that I show you here. Basically, what I took here, I took all 10 pulses or bursts of these DLP earthquakes that we identified during 3.5 years beneath the chaîne de puits, you can see. And then I took just 1 hour of data from Kamchatka, this black signal. Okay. And I plotted, I took stations approximately at the same distance from the hypocenters, and I plotted this on the same scale. You can see this is much, much bigger. The energy of the signal is 50 times bigger than all this. This basically indicates us that the activity that we observe today in the chaîne de puits is weak. And more recently, we have confirmation that this kind of weak activity has been recorded even by some past stations, maybe 20 years ago. So basically, we see some background, maybe refeeding of magma, but not its acceleration that can immediately lead to the eruption. Okay, so this is a simple way to answer this question. Compare signals from different volcanoes with each other. But still, we would like to get real quantitative answers. Okay, and this will be the last part of my talk. So how can we possibly estimate volumes and supply rates? And the idea for this is that, as I told, with focal mechanisms, we can believe that these earthquakes are dominated by volumetric component, which is also logical if we consider they are created by magma. Basically, if we have some magma injected into a system, it causes the volume changes. And so the seismic signals that we observe are mainly caused by these volume changes, not by shear stresses, like in case of regular tectonic earthquakes. So in case of mechanisms dominated by volume changes, we can write seismic moment tensors. I show it for 2 simplified geometries, spherical, which is obviously not realistic, and another that it might be much closer to what happens in the real volcano, tensile crack, that if it is oriented horizontally will be called by volcanologists seal. If it's oriented vertically, it will be called by volcanologists dike. But in any case, if we write the seismic moment tensors, they will be also always proportional to the change of volume. And scalar seismic moment in both cases is written like this. It is basically product of bulk modulus of surrounding rocks by the volume change. Okay, so we have this very simple model. So if we can measure seismic moment for an earthquake, we can immediately estimate the associated volume change because we more or less know the bulk volume, more modulus of S rocks. Okay, and I tried to apply this to our catalog that we obtained in Kamchatka. I took only the part that preceded the first unrest, so till December 2015. And I took magnitudes that were determined by Wavefund. I applied this Kanamori formula to convert magnitudes into seismic moment, and I applied this formula, so we can see that cumulative seismic moment is going like this. And then if we apply this formula, we have cumulative volume. And here's our final estimation of volume. If I divide this by the 3 months, it gives us this kind of rate. And this is too small. It's basically 3 or 4 orders of magnitude from what I have shown you. Kamchatka, we know it's very active magmatic system. We expect rather something closer to 1 on 0.1 kilometer cubic per year. Okay, so why do we so hugely underestimate? Okay, first reason can be actually our physical model of the earthquake. Basically, our physical model of this earthquake was that we considered very quick magma injection that created this volume. Basically, very quick means co-seismic during less than second. So basically, everything injection and volume change was co-seismic, and all these generated seismic waves that we measured. But actually, we can have other scenario or model that was suggested by Oleg Melnik and that we published together. Basically, it considers two-step process. First, we have rather slow injection of fresh magma. Slow means aseismic, so it means it takes longer than a few seconds, so it doesn't generate significant seismic waves that we can uh, record. It creates this new volume delta V, but then this magma is saturated in gases. So it's basically like a champagne bottle. Yeah. So, and at some point, this oversaturated magma, if by some small pressure change, can trigger this outgassing, and the gas bubble starts to grow. And what has been shown in this publication, that process is actually very fast and takes less than 1 second and really generates seismic waves. But in this case, the seismic moment will be related to this volume, not by bulk modulus, but by this parameter, uh, 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 gas overpressure in the magma, that, again, volcanologists with some knowledge of rock physics estimate of the order of tens of megapascals, which is much less than bulk modulus of the rocks. And so when we apply this model to the same data, we end up with much bigger estimation of magma supply rate, which is much closer to what we could expect to this in this volcanic system. Still, seems to be small with respect to what I have shown you before. So what can be another reason?
Nikolai, sorry,
Yes.
sorry, it's Chris. And anyway, your talk is so clear that I haven't had a chance to keep up with everything to ask a question. But can you say just a little bit more about the DLP magnitude? Where does this magnitude come from?
Oh, it's a good question. So, yeah, um, it comes with these magnitudes were computed based on some regional magnitude scale, which is obviously has not been calibrated with volcanic earthquakes.
Okay, but so it's like a surface wave magnitude or something, or
No, it's not surface wave. It's no, it's regional or local magnitude scale. It's kind of ML that they use in Kamchatka.
yeah,
But
yeah.
again, it has been calibrated on tectonic earthquakes.
Okay, okay,
So in one walk, we compared these earthquakes with, we tried directly from waveforms estimate moment magnitudes, and we compared the two. And I mean, they are not orders of magnitude apart. So
Mhm.
these magnitudes, I would say, not very good, but they are sufficiently good to the exercise that we're doing here when we just want to obtain order of magnitude estimates.
I see, I see. Okay, thank you. Yeah, we'll come back to the connection to moment then in the discussion. Yeah, thank you.
Okay, so next issue with our signals. Actually, as I have shown you, this DLP occur in bursts. Okay, and for example, in this burst, there are, I don't know how many, maybe a few hundreds of deep long period earthquakes. But when we do this, even the best possible AI detection, we can only identify those where we can have P waves, and for most of them, we don't see P waves. So basically, uh, uh, one possibility is that uh, when we represent this kind of seismic signals with a discrete catalog, we lose significant part of energy. Okay, so this means that at some point we need estimate not magnitudes of few earthquakes, but somehow equivalent seismic moment for the whole sequence. And this is even much more challenging than we just discussed with Chris. But still, I tried to do it. Okay, I didn't do it for Kamchatka because in Kamchatka we have also this mixture of deep and shallow tremors, and it's separating them is not straightforward. So to try this exercise to work with tremors, I selected another volcanic system. So it's in Alaska. It's called Katmai volcanic cluster. Okay, and it's famous for this eruption that maybe some of you heard about, the Valley of Thousand Smokes. It's actually uh, just the biggest eruption ever occurred on Earth since the beginning of 20th century. Okay, so it was really huge eruptions. But today, this volcanic system that contains many volcanoes, shown here with the red points, is rather quiescent. Okay, but there was a recent volcanic unrest in 2022. Okay, this is the catalog of Alaska Volcano Observatory that shows number of earthquake beneath this volcano Trident, one of volcanoes of the group, and suddenly it hugely increased, and it was a lot of shallow seismicity and usual during unrest. But then there was this very interesting episode where seismicity migrated through the whole crust. But then at some point there was this activation of this cluster that are DLP earthquakes, and they are shown here. They're really located between these main volcanoes, Trident and Nova Rupta. Nova Rupta was actually the source of this huge eruption. I mean, the volcano that generated this source. So what we did, we took this catalog and we applied the same equation. And we actually estimated this volume. You see, 10 minus 4 kilometer cube, which is, again, if we compare with this kind of eruptive, I mean, magma supply rates, it's really small. So when we use the catalog of discrete earthquakes, we underestimate most likely the volumes. So, but then we also in Grenoble we applied again the same method for detecting tremor to this data, and we actually have seen that this deep seismicity is mostly composed of these short bursts of tremors. Short here means like few minutes, from 2 to 10 minutes. You see, this is not an earthquake. It's a tremor episode. You see, it's 600 seconds, 10 minutes. Okay. So, and what is good at Katmai, there is no shallow tremors. Okay, so it's quite easy to detect these tremors and work directly with the signal. So we could combine this tremor catalog. It is shown here. Basically, if we show some average location of these tremors, they're really located in this near this crust mantle boundary where we're really interested in, and then the occurrence rate is shown here. So the red line is deep tremor detections. What is shown here, then we can compare them with deep earthquakes, this thick gray line, and we can see that they temporally they show very similar pattern. Basically, there was this huge activity during just a couple of months around July 2023. Okay, and but then when we apply the same equation from Melnik, but now to seismic moment estimated from tremors, we obtain very different figure. And this figure is actually seems to be much closer. This number seems to be much closer to what we expect from geological data at this volcano. Sorry, where I have this. Yeah. So basically, here is the magma supply rate expected for this volcano. I mean, it's plus minus. But basically, what we have seen, this was a unique episode that occurred during more than 20 years of observations. Outside these 20 years of observations, there was no significant deep long period volcanic activity. And we can assume that maybe these kind of episodes are rather rare. For example, once a century. If this is once a century, so if we multiply this by 100, we will get something very close for 100 or for tens of years, we will get something very close to this number. Okay, so basically, it seems that we are not so far from correct numbers if we apply this. Okay, so and final slide. Finally, I tried to apply this to this Massif Central data. And again, if I use the model based on bulk modulus, I obtain very small values. If I use model of Melnik, I obtain larger numbers. And then if I extrapolate these numbers over the duration of existence of these volcanoes, I obtain something like this 5 kilometer cube. So, and but from known eruptive rate and this extrusive intrusive ratio, we would expect something like 100 kilometer cubes maybe. So we it seems that there are two possibilities. Either we still underestimate somehow what happens, or it may be that right now, because we're in this quiescence period, the magma supply is not so active, and maybe at some point these volcanoes will it's reactivate at depths, and we may expect to detect much more of this deep long period seismicity. And if we at some point detect it, this is when we need to start to be worried. Okay, so I think here my conclusive remarks. So on, I think this scenario that on active volcanoes the LP seismicity uh, are related to deep magma supply rates is plausible. Okay, at least we cannot ignore it. We need to explore it to try to get estimations. So then another important conclusion is that earthquake catalogs is good, but on volcanoes we also have a lot of tremors. So if we need to estimate the full energy of phenomena, we need to work with tremors. So this is what we need. And obviously to to have real quantitative estimations, we need physical sources, uh, physical models of sources. Okay, and here I just explored basically one model. It's a model. I think in literature there were other models proposed, and we need to test them. Okay, and then some challenges is that yeah, estimating seismic moment of continuous tremor. I did it somehow, but I don't pretend to be very accurate. And then also another issue is that volcanic media itself is not homogeneous. It's strongly heterogeneous. We have strong wave scattering encoders that can also strongly bias interpretation of waveforms. So, and this is why I think at some point we really need to combine seismology with physical models of volcano interior. Okay. And I think here I will stop. And thank you for your attention. And I'm ready for your questions.
Fabulous talk. Thank you very much, Nikolai. I will invite people to unmute themselves and join me in thanking Nikolai. Well, let's give him a minute to catch his breath and have a drink. And yeah, and then I'm going to recommend that people just use the raise hand feature at the bottom of your screen. I think it's the easiest way to put ourselves in order and to organize a way to
Okay, so you will give you will organize this, yes, Chris?
yeah, sure, I can do it, or you kind of,
Okay.
but it's probably easier if I call on people
Yeah.
just to organize things so you don't have to do it, Nikolai. And we already have many people who are helping out and organizing things. And so let's go ahead. Joan Gomberg, please go ahead.
Was great talk. Thank you. So I have a question about dynamic triggering, and it's long reported that these volcanic systems are highly sensitive to dynamic perturbations. And particularly after the Kamchatka earthquake last year, for example, there was talk about volcanic activity in Kamchatka increasing. And it seems like what you've done is a really good way to sort of test that. Have you looked, particularly in Kamchatka, was there increases in any of these metrics suggesting that magmatic activity was mobilized following earthquakes, or elsewhere for that matter, retrospectively?
Okay, there are a few questions in one, but I will try to answer. First of all, I personally did not